Hey everyone, I hope you all are safe and doing good. So I hope you are done with bubble sort. Now we'll see next sorting algorithm, that is insertion sort. It is also comparison based sorting. We compare the elements. How we do? Why it's insertion sort? We insert the data. So it's like how we insert in an array. If so, suppose sorted array is given to you, right? This is sorted array, and now you are supposed to insert. Suppose 4. 4 you have to insert. How you will insert in a sorted array? First, you have to find out the correct position. So find out which is the correct position for this. Like compare this. 4 is greater than this, go right. Greater than this, yes, go right. Less than this, yes. So this is the correct position. Here I'll insert. But directly, obviously I cannot insert here. Second thing, after finding out the correct position, we shift these elements there. So we shift 25 here. We shift 20 here. Then 17 here. Then 15 here. Then I'll insert here 4. So like this we have shifted 1 to the right. And then we insert. Like this we insert in an array. Yes. So shifting is also taking like how many elements you need to shift at in worst case n elements, because suppose I want to insert 1. So 1 I'll insert here. So you have to shift all the elements 1 to the right position. So it's n. Time complexity would be order of n. Shifting. Yes. This is how we insert basically. If a linked list is given, suppose this is a linked list 1, 3, 5, 7, and I want to insert here 11. It's a sorted linked list. First you have to find out the correct position, same correct position. Start from here. Because we have head of the linked list, we traverse this. 11 greater than this, 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 less than this. So obviously it is greater than this but less than this. So here I can insert. For insertion, you need to update these pointers and that's it. For insertion, there is no shifting you need in linked list. Only you need to traverse. So traversal is also taking like order of n time. But shifting is not required in linked list when you insert. Insertion. So that same kind of process we do insertion kind of thing, right? To sort a given data or a given array or a given list. That's why the name is insertion sort. How we apply this process here? See, suppose this array is given to you. So here you don't need to find out the correct position. We have to sort it in ascending order, right? So we start from the second element. We divide this given array into two portions, sorted and unsorted. So first, we have only one element. So I know if you have only one element, that is sorted. No need to do any sorting. So I'll start my loop from here, from 1. 0th element, I will consider that is a sorted portion. And this is now unsorted portion. So I will sort only this portion. How you will sort? See. One by one, I'll take element from here. So first I'll take 4. Okay. Let's assign, we have a temp variable I'll take and there I'll store this 4. Now what I do is, I compare this element with its previous elements to find out the correct position for this to insert. This is how we insert. So this now compare only we have in sorted portion we have only one element 5. So we compare this 4 with 5. This 4 with 5. Yes, this 5 is greater, this 4 is less. If this is less, then you have to find out the correct position. So how you insert? We do is we shift this 5 here. Because you can consider I just take out this 4 here. So this is kind of like garbage value for us. Because I have this 4 in a variable. If I need 4, I can directly fetch from temp variable. So this is for me garbage value, or you can say it's a blank space, empty space for me. Consider this. So yes, my 4 is less than this, whatever is in sorted portion. It's less than 5, only one element we have. So we swap this 5 here. Sorry, we shift this 5 here. So the array is something like this. Now we have 5 is here, 10 is here, 1, 6 and 1. It's not that after shifting just place this 4 here. No, wait. Now, is there any other remaining element in the sorted array? So with that, I can compare this 4. No. It means, yeah, this is the right place for this 4. Insert 4 here. Okay. Now, this is my sorted portion. because I'll start from here. So then I guess the loop would be plus plus. So now with 2, now my I is here. So this is my sorted portion now, and this is my unsorted portion. Again, now we take 10 element, 1 element this. So now in temp, I'll store 10. Keep comparing with the previous elements. So it's not that now I have 2 elements. So you have need to compare 10 with 2 elements almost, maybe in worst case. So it's not that I'll start from here. Compare this with 4. It's greater than this, like this. No, because I will not compare with this, because we need shifting from this element. If you need shifting, then you need a shifting of this element this, then this element this. So we start comparing from here, from here, from this, then this, like this, reverse direction. So for sorted array, we go from here to here, reverse direction till the 0th index. From unsorted portion, we go from here to here at the end, like this. So first, compare this 10 with 5. So suppose this is whole for me. 10 with 5. Do you need any shifting? No, 10 is greater than 5. So no shifting is required. 10 would be here only. So I'll insert 10 here. Whatever right now, at suppose this loop will be handled by I variable, this loop will be handled by j variable. So I will move from here to here, j will move from here to here. So 5 is not, like you can say, j is right now this. So this 5 is less than this 10. So no shifting is required. So I can simply insert 10 here. That is at whatever at j plus 1, I'll insert 10 here. So 4, 5, 10, 1, 6, and 1. Now, this is my sorted portion, and this is unsorted. Now, I'll take this variable 1. So, now in my temp, I have 1. Now, start from here comparing. This is kind of like whole for me. And see, here, this was my first pass, pass 1. When we have taken 4 here, then we compare this with this, we shifted this, and then 4 becomes here. This was sorted after first pass, and this was unsorted. 2 elements were sorted. So that is pass 1. Now in second pass, we take this 4 here. So this is pass 2. And we compare. But here, fortunately, because we were lucky, so we need no shifting. Right? So directly we store 10 here. So after pass 2, this is my sorted and this is my unsorted. Now let's take pass 3. So I'll just write down again here. Now after pass 2, this is sorted. This is sorted and this one is unsorted. This is my pass 3. In pass 3, I'll take temp. In temp, I have 1. I have 1 now. Compare. 1 with this first 10. 10 is greater than 1. Then we need to shift. Now shift this 10 here. So now my array becomes 4, 5. Here we have 10, 6, and 1. Here we have 10 actually. We have shifted this 10 here, but still we have 10. But for now, to get you a better idea, I just consider this is nothing here. I'll not directly put here 1. No, this is not. I don't know that this is the correct location. Still, we need to find out, because still there are few remaining elements we need to compare. Next, we compare with this 5. 5 is greater than 1. Again, shift. So we shift here. So now my array becomes something like this. 5 is here, 10, 6, and 1. Can I insert it directly 1? No. Still there is one element 4. Compare this. 1 with 4. 4 is again greater than 1. Again shift. So we shift again 4. 4 would be here, then 5, then 10, then 6, and then 1. Now, do you have any other element to compare this with 1? No. Now that is the exact place. Insert 1 here. Yes. Now, sorted portion is this. After pass 3, this is my array. Next pass. Pass 4. Now my array is something like this. This is sorted portion, this is unsorted portion. Now I'll take this. So in my temp, I'll just store 6 and I'll consider that this is like garbage for me or a blank space. Now start comparing with 10. 10 is greater than 6. Yes. Shift this 10. So after shifting, array becomes 1, 4, 5. 10 would be here and 1. I'll just leave it blank. Although we have 10 here, but I'll just leave it blank. Can I insert 6 directly here? No. There are still remaining element left to compare this 6 with. Now compare 6 with next element, that is 5. J minus minus. 5 is less than 6. So no shifting is required. Definitely this element would be after 5. So whatever, right now j is here. So whatever at j plus 1, insert the 6. Now I'll insert 6 here. So now the array becomes 1, 4, 5, 6, 10 and 1. Now this is my sorted portion. This is unsorted portion. Now next pass 5. I'll take this. Now erase this. 1, 4, 5, 6, 10 and 1. I'll take this. Only one element we have in temp. I have 1. So this is like blank space for me. Compare 1 with 10. 10 is greater than 1. So definitely 1 would be here before 10. So we shift 10 here. After shifting, it becomes 1, 4, 5, 6. We shift 10 here. Do we directly insert 1 here? No. What should be here? So it's like you can say blank for us for now. Next element is 6. Compare with this 6. J minus minus. After doing J minus minus, 6 is greater than 1. Shift. Now my array is 1, 4, 5, 6 and 10. Here, what is there? I cannot insert 1 here. Still there are remaining elements. Compare with this 1. 1 is greater than, compare with 5. 5 is greater than this 1. Yes. Shift this 5. After shifting, array is 1, 4, 5, 6, 10. Next 4. Compare with this 4. Next element is 4. So compare with this 4. 4 is, yes, greater than 1. Shift. Shift this 4 here. So 1, 4, 5, 6 and 10. Now here. Remaining element is 1. Compare 1 with 1. Both are equal. So it's like we don't shift. Now, if this one is greater than this, then only we shift. But this is equal or less, stop. Now directly whatever, right now my j is here. J is here. So at j plus 1, because we have a space, insert, that is the correct position. Insert this temp. So insert 1 here. And now I got sorted array. That's how we insert. So basically, we take one element at a time from unsorted portion. We find out the correct position in sorted portion by shifting elements. Then we insert at the correct position in the sorted array. And we repeat the process till we get the entire list sorted. That is insertion sort. This is stable. If you consider here 1A, 1B, every time the order would be at last, it's 1A, it's 1B, right? And see, it's 1A, 1A. So we didn't swap, or you can say that the relative ordering is as it is. We didn't switch the order. So 1A is before, 1B is after. So every time 1A after sorting also 1A would be previous one, before that 1B. So not actually 1A, 1B, because the value is 1, 1 only. But the relative ordering would be exactly same. So it's stable. Insertion sort is stable. Now let's analyze this. Okay. How many passes? 1, 2, 3, 4, 5 passes. Elements. How many elements? 6. Passes you require 5. So basically n minus 1, same. Number of passes required are n minus 1. Yes? Okay. Next thing. Number of comparisons. In pass 1, how many comparisons? Because in sorted array, now I have only one element. We start from the second element, we assume that this is my sorted array. So we need only one comparison. That's it at max. So in first pass, one comparison. In second pass and swap, number of comparison, number of swap. Number of comparison 1, number of swaps at most 1. Okay, or the shift just 1, because ultimately what we are doing is, I am saying we are shifting, then we are putting this 4 here, but actually we are just swapping this. See, after sorting this, 5 would be here, 4 would be here. So we are actually swapping only. Number of swap is also 1. In second pass, number of comparison 2. This is the data, then we compare this, then this. At max, we need to compare. At max, in worst case. Number of swap is at max 2. Number of swaps are also 2. At max, in worst case, I'm just telling, not, I'm just saying that, yeah, you need 2 comparison, you need 5, you need 2 swaps. No. In worst case, you need this. Because obviously in past 2, there was 10, and we compare only one time and we got that, okay, don't need to compare with this 4. But maybe at worst case, we need to compare from here till 0. In past 3, how many comparisons? In past 3, we take 1, we compare with this. 3 comparisons. So in past 3, I can write here number of comparisons 3. Number of swaps would be in worst case 3. In past 4, number of comparison 1, 2, 3, 4. We compare with this at worst case. So 4. Number of swaps are also 4. In this number of comparison 5. Number of swaps also 5 in worst case. If we calculate total number of comparisons, then we add simple. So 1 plus 2 plus 3 plus 4 plus 5. It's like something like this. So 5 means n minus 1. So number of comparisons are 1 plus 2 plus 3 plus 4 for n elements till n minus 1. We keep adding this. Same formula. So same order of n square. Number of comparisons are at max this. So time complexity would be same n square in worst case. Right? Okay. Number of swaps are also same. In this 1, then 2, then 3. So same 1 plus 2 plus 3 up to this. So n square, number of swaps. But basically we need number of comparisons to find out time complexity. Right. This is stable. Is this in place? Yes, you don't need any extra space. Within the given array only we are doing some shifting, swapping, and that's it. So it's in place. Space complexity for this is order of 1. Yes. So it's in place. Is it adaptive? Let's see. If my array is something like this, already sorted. At first, I'll just take this is my sorted portion and I'll start from the second element. So I'll take 5. In my temp, I'll just take this 5, compare 5 with this. Do you need shifting or swapping here? No, because 2 is less than 5, so no need to do swapping. Just place 2 here. Sorry, 5 here itself. 2, 5, 7, 8, 10, and 15. So this is my sorted portion now, and this is unsorted. Okay, before discussing it's adaptive or not, let's write down the code for this. Then we see that this one. So same here also we need 2 loops. One will handle the number of passes. Second will handle the number of comparisons. So outer loop will handle number of passes. That will run till n minus 1 time and we'll start the loop from here. I told you that the first element we assume that's already sorted. So we start from the second element. So we start from 1. Okay. So the outer loop. We start I is equal to 1 and I less than n and I plus plus. It's not n minus 1. It's less than n because n is 6. So I want that it should run for 1, 2, 3, 4 and 5. 5 times. Yes, because there are 5 passes we need to sort 6 element in insertion sort. So less than 5. Now after that what we are doing? We are taking a variable int, temp. So we take temp is equal to whatever the at ith index, whatever we have, we just take in temp. And then j is equal to I minus 1. Yes, because j loop will start from here and will run from here. So j would be I is here, so j would be 0, I minus 1. If I is this, they should be starting from 1. If I is here 3, I mean, I'm taking 1 here, so j should start from 2. So I minus 1. Now, we keep comparing till what? Maybe in worst case when j becomes till at 0th index. One condition is this. So I can write down simple this. There are two conditions. So we use while loop. So we use here while loop. While inner loop. While j is greater than equal to 0 and 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 this element, it's not that we keep comparing. No, sometimes we don't need to compare with till 0. In this case, when we have taken, it was 10. So we compare with only one time and we got to know that we don't need to compare till 0. Okay. So second condition is greater than equal to 0 and array of the element whatever at jth index right now is is greater than 10. Whatever at j was at first 0. If this element is greater than temp at first in first pass, in my temp I was having 4. If this element is greater than temp, then only we shift this element one position after. So at whatever element now at jth index, I'll assign that element to j plus 1 index. Yes, we shift that, right? And then I'll do j minus minus. After completion of this while loop, the inner loop, after completion of comparison, we got the right position. And where is the right position? We know that I've told you. Whatever at j plus 1 place, there just insert the stem. That's it. This is the code for insertion sort. Yes, because I guess you got. Now you can easily dry run this. So you take a this you can say example and dry run this with code. I have already discussed how you will dry run this, how the things are working, and the code also. So I hope you got it. So you can easily dry run this yourself. Right. Now, the best case. Okay, let's see. I was discussing this thing. The best case, it's already sorted. Right. Now this is sorted portion, this is unsorted. So we take this in temp, we'd compare this with this. Do you need swapping here? J is less than, okay, 2, 5, 7, 8, 10, 15. Let's dry run this for the best case and then you will get to know it's adaptive or not. At first my I is 1. So I'll start from here. I is 1. I less than 1, yes. In temp, I'll start whatever at this. So in temp, I'll store this 5. And j is I minus 1. So j is here. J is here, I is here. While j is greater than equal to 0, yes. And ARR of j greater than temp. Is it greater than temp? No. So we'll not enter in this while loop. Yes. So we will not enter like in this while loop. Whatever at j plus 1. J is right now 0. J plus 1 is 1. We index whatever at temp. In temp, I have 5. So I'll insert 5. It means like 5 is already there. So no need to do any swapping kind of thing. So after this, my array is same 2, 5, 7, 8, 10, 15 after first pass. Now I'll go here and I plus plus. At I becomes this. So my first pass is done. In first pass, my done. First pass is done. No swapping we need. We just compare with one comparison we need. That's it. Only one comparison. Second. So this is my sorted portion. Now my I is here 7. So I'll take temp. In temp I have 7. J is equal to this. So my j will start from here. My I is here right now in second pass. Compare. J greater than equal to 0. Yes. ARR of j 5 greater than temp. No. So we'll not enter again here. Whatever at j plus 1, insert this temp 7 as it is. So it's 2, 5, 7, 8, 10, 15. Now this is my, I'll assume sorted portion because now next iteration is I plus plus. So I becomes now, I will be here. 1, 2, 3. I becomes 3. At first I was 1, then 2, now I is 3. So I is here. So in my past 2, also how many comparisons? Only one. Only one comparison. Here also only one comparison. Swapping, no swapping. Swapping, no swapping. Now in past 3, same. In temp, now I have 8. J is equal to this, I minus 1. J greater than equal to 0? Yes. Is array of the J element is greater than temp? No. So do not enter here. At J plus 1, insert directly temp 8, same as it is. So 2, 5, 7, 8, 10, 15. Right? So this is, now I becomes 4. So 0, 1, 2, 3, 4 here. So till now we have sorted array. So in pass 3 also only one comparison and no swapping. Now I have pass 4. After any pass, can you say in this, let's take in this case, after any pass, can you say like, okay, after this pass second, I have this array, sorted array. Can you say, okay, the minimum element is this or the maximum element is here at the end of the array? No, because I don't know what is the next element and where the next element would be inserted. Next element is 1. So I cannot say minimum element is at the first because after 1 should be here. Maybe after that I'll have 15. So I cannot say maximum element is here in the sorted portion because 15 would be here in the sorted portion. So in insertion sort, we cannot guarantee this thing. In bubble sort, guaranteed we can say that first pass, the largest element is at the end. Yes. But in this case, we can't say something like this. We are not sure. Yeah, we have sorted portion, but we are not sure that smallest element is in the front or largest element is at the end. No, we don't know. Right? Now, see in this case. Next is in pass 4. I is 4, I is here. So in temp, I have now 10. J is equal to I plus 1. So J is here, I is here. Compare. J greater than equal to 0? Yes. Is this element greater than temp? No. So no need to enter into while loop. Simply J plus 1 is equal to temp. It's already there. 2, 5, 7, 8, 10, 15. Now again I plus plus. I becomes 5. That is this. So this is sorted. How many comparison in pass 4? Only one. Swapping? No, no swap. Now we have pass 5. So in pass 5, I is here. In temp, I'll have 15. J is equal to I minus 1. J is here. Compare. Is this true? Yes. Is the second condition true? No. 10 is not greater than temp. So we don't enter again here. Again insert temp here. And after pass 5, the array would be completely sorted. And I plus plus I is 6. But now it's not less than 6. So out. Even if the array was sorted, but still you had to go through all the passes. Yes, you had to go through all the passes. But number of comparisons, if you check number of comparisons, in every pass only one, here only one. So only it's like 1, 2, 3, 4, 5 comparisons total. In best case is obviously this array is already sorted. That is the best case. If array is in descending order and you have to arrange it in ascending order, that would be worst case. So in this case, we need 5, almost n minus 1 comparison. So in best case, time complexity is n square. Best case time complexity is, n for insertion. Worst case we have seen, you need to compare till 0. Okay. So it's n square. In average case also, it's n square. So yes, we can say that it's adaptive. It's by default adaptive. We haven't tried like in bubble sorting, we add some flag variable to make it adaptive. In this case, it's not the case because it is taking advantage of the sorted array. We don't need any comparison, more comparison. In every pass, only one comparison. Although the passes are obviously 5 passes, but within the passes, we know this how many times this inner loop will execute. That will give you number of comparison, and that will give you time complexity. But the number of time this loop or this how many time this comparisons are there, only one time. Only one time we are comparing this and this because the conditions are not true. We not enter here. Only one time in every pass. 5 passes, 5 comparison. 6 passes, 6 comparison. 10 passes, 10 comparison. Almost. Okay. And passes are n minus 1, so n minus 1 comparison. So n. So that's why when array is sorted, so it is taking advantage of that thing, time complexity, or the time is decreasing according to that. It's n. So yes, it is adaptive. Yes, it's stable. Yes, it's in place. Space complexity is 1. Okay. And in best case, number of swaps, if anybody asks, no swapping. We haven't swapped even a single time because there is was already sorted, so no swap, zero swapping. Number of comparisons are n minus 1, but swap is 0. In worst case, swapping is a n square, same as number of comparison. But this is also same like good for small data set, right? Not very large, only 10, 15 or 50 elements we have, then only, I guess, right? Not more than that. Plus nearly sorted data, if you have almost sorted data, then it's good. But if you have large data set, random data, it's not at all good because time complexity is n square. So now you try this out. You pause the video and try to write down the code. Okay, so I'll create a new package here, sorting algorithms. And within this package, let's create a new Java class. Okay, we are discussing here insertion sort, right? Let's take an array first. 161. I'll call insertion sort and I'll simply pass array, or you can pass the size as well because we want. So arr dot length. Let's pass the size as well. Let's define it. Make it static because I haven't created any object of this class. Static and insertion sort void type. First, I'll have an array, then size. Let's suppose n a variable I'm taking. Now, okay, for loop at the very first. I'll start from the second element, that is whichever at the first index. I is equal to 1, I less than n, and I plus plus. Now we take a temp variable and there I'll store whatever right now at ith index. I'll store that. Now I'll take j is equal to, I'll initialize I minus 1. Now next loop, while my j is greater than equal to 0, 0, and second condition is whatever at arr of j, it's greater than whatever you have at temp. If this is true, then we shift, sorry, whatever at jth element, that I'll assign where at j plus 1 index. Whatever at jth right now we have, that I'll shift to the right at j plus 1 index. And now I'll decrease j. After this while loop means we got the correct position, and the correct position is j plus 1. So whatever at j plus 1 in array, I'll just insert whatever in my temp I have right now. That's it. So yes, we got it. And at last, we can simply print array. So we can't simply print here whatever arr, right? To print it, either you can directly call from arrays dot toString method. This will convert this array into the string representation and that it will be printed. Or you can just write down a loop, for each loop or simple for loop, and with one by one from index 0 till the end of the array, you keep printing the element. It's up to you how you write down. I'm just using the inbuilt that toString method from arrays. Let's run this and see. So it will give me 1, 1, 4, 5, 6, 10. So it's 1, 1, 4, 5, 16, right? That's how we do insertion sort. It's easy one. If you want to debug, you can just add some breakpoint here in this and you can just try to debug this. It's up to you. Okay. You dry run this as well as you try to debug this. Right? At first array is this, n is equal to 6. So if you step over, then in temp what I have right now, in temp I'll have 4. Yes, that's exactly I want 4 in the temp. Yes, now we compare. J greater than equal to 0, yes, true. Then next condition is also true. Then we swap. See. Now, here we have 5, here also we have 5 because 4 is in the temp now we have. Okay. So, the both places right now at this point array is 5, 5 and j minus minus. So, do j minus minus. Now, j greater than equal to 0, no, that's false. So, we out of the loop and j plus 1. Now, we insert whatever at temp. In temp, we have 4 and j is right now 0. So, j plus 1 at 1 index. Here, you will get now 4. When I step over this, this will be changed. See, sorry, here, j is 0, but j becomes minus minus, so j becomes minus 1. So when we go for j plus 1, it becomes minus 1 plus 1, that is 0. So at 0th index, I'll insert 4, not at 1. Okay, now next iteration. Like this, you can just try out yourself. You can debug this. Okay, so that's it about insertion sort. I guess we have discussed everything, the process, what is the algorithm, the steps, and we have analyzed it also, time complexity in all the cases plus space complexity. How we find out time complexity, that also you get. In the next lecture, we'll see now what is selection sort, right? And see one more, this insertion sort is basically good for linked list as well because there in linked list we don't need any shifting. In arrays we need shifting. So you can apply this for linked list also. It's more good in for linked list than arrays. Now in the next lecture we'll see selection sort. So now it's in the next lecture. Till bye. Take care.